I learned that. I looked at Russian papers. Asked them they had anything to do with everybody's name. That's what the money but I have to have was that big. So you read Russian? No.
Okay. Let me have your attention. Let's get started. Let me have your attention. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. John Sheffield. He is a senior fellow with the Joint Institute for Energy and the Environment, which is a local organization consisting of the University of Tennessee, TVA, and the Oak Ridge National Laboratory. John received his PhD from London University in physics in 1966. He had already begun his career working for the United Kingdom Atomic Energy Authority in 1958. He was there at the Harwell Laboratory until 1966. In 1966, he came to the United States and was on the faculty of the physics department at the University of Texas, where he stayed until 1971. And then apparently didn't like being in the States because he returned to the United Kingdom for just a few years. Worked again for UKAEA, the United Kingdom Atomic Energy Authority, from 71 to 77. And then he decided, yes, I do want to be in the United States, and he came back in 77, and he's been here ever since. He joined the Oak Ridge National Laboratory in 1977, and where he was until he retired in 2003. And during the last 6 years of that tenure, he was the director of the Joint Institute for Energy and Environment from 1997 to 2003. The title of his presentation today is Future Energy Demand Supply in Developing and Transitional Countries, including China, India, and Korea. Ladies and gentlemen, please welcome Dr. John Sheffield.
Thank you, Lee, and thank you for the opportunity to give this talk. I actually didn't write it down correctly on here, probably because I had it for another talk some time ago. Helped organize a very interesting meeting at the Max Planck Institute in Garching in Germany back in December, and the meeting actually was development in fusion power. What role could fusion energy power play in transitional and developing countries? And included in that, what we did was we asked people from China and India to come and tell us what they plan to do in those countries for energy, and did they view fusion as being useful. But out of that then came an incredible amount of information about energy demand generally and prospects in these major countries. The work was supported by the European Fusion Development Agency, and my good colleague Thomas Hamacher in Garching was the key organizer. I helped support him, and US DOE Office of Fusion Energy Science supported me. The reason that these countries are interested in fusion, and in fact in any energy source, is they're experiencing absolutely dynamic growth in their general GDP. Unfortunately, at the same time, they're also got a large increase in population, and because of this, and because they want to raise their standards of living, they're going to need a heck of a lot more energy per capita per year. That's the simplest way to look at it. They're going to need triple or quadruple energy per capita per year. And that is expected to continue through the next century. And when you look at the numbers, which I'll show you, they are staggering for what they have to install in terms, particularly of, say, electrical capacity. One very important thing is that international collaboration, in their view, is critical to this, because it doesn't matter whether it's fission or fusion or fossil or renewable energies. They're going to need the latest technologies. They have to be a part of it. And so that's what we'll look at. We have a distinguished group of people, including Naki Nakachenovic from IASA. He's the guy who put together the global scenarios for the International Panel on Climate Change. He's one of the world's experts on this, and he gave a fantastic talk summarizing. I think he had 300 slides, and I've stolen some of them from him. We had Professor Huo from China. He is there represented actually on the National Thermonuclear Experimental Reactor program, and distinguished professor, very interested in the whole energy area, Professor Shukla from Ahmedabad in India, who does system studies for the Indian government. Unfortunately, last minute, his government told him he had to do something else and he couldn't come, but fortunately we had all his photographs and people in Europe about. John Clark from PNL has been doing studies with them of nuclear fission power in the world using the Edmonds-Reilly models that some of you may have come across, looking at the deployment of fission. And then we looked at fission power in Korea because it's a very interesting example of how a country that was an agricultural society back in the 50s and 60s actually now makes top-level nuclear plants for itself. And that's an incredible development and a good omen for these other countries. Then we had Dr. Cato from the IEA gave a very interesting talk on investment issues and so on and so forth. Talk on the availability of oil, fusion, and then issues of geopolitics and proliferation. Just to give you a feeling for what changes one might expect, this is a very interesting chart. This is the last 200 years. And population grew 6 times, life expectancy grew twice, work hours per year dropped, mobility increased by 1,000 times, income increased, energy use went up 35 times, and so on and so forth. So in 200 years, you had incredible changes. So it shows what can happen in the world. Nobody expects that kind of rate of change in the next century. Hopefully we won't have to do that. But there can be a major change. Second, over this period from 1850 to 2000, you can see how the different energy, I can't do that, can I? No. You can see how different energy sources have changed, like oil, for example, and gas, and then, of course, the buildup of nuclear. And the buildup of nuclear is a good example for the rate at which energy systems can come into play in a massive amount. And the same will be true for others as well. So you can have a rapid change in the sources of your energy. Oil has taken over in recent times, and in fact will continue for a long time. What about population? Well, there are large numbers of population projections from all over the place, but the average, the typical is that population will go up to something like 11 billion, plus or minus the odd billion, by the end of this century, from where it is today at about 6 billion. So it's about a factor of 2. And with that, you can inevitably going to expect a large increase in energy demand. In looking at all of this, the International Panel on Climate Change, in order to study what's going to happen to emissions of greenhouse gases, has commissioned a large number of studies, projections of what different parts of the world might do, and in total what the world might do to meet the demands of this increase in population. They've done at least 40 scenarios. That's one factor, and we'll see what they show. The second one is that over the period up to 2030, the IEA projects that 70% of the demand growth for energy is going to be in the non-OECD countries, in other words, the non-quote developed world, the transitional developing countries, and 20% of that increase will be in China alone. And I'll show you what the numbers are for that. In order to meet the kind of situations the IPCC considers, where you're going to have an increase in energy demand, but at the same time you've got to have less emissions, we're going to have new and carbon-free energy sources on a scale that is mind-boggling. And through all of that, there's going to be a huge increase in demand for electrical capacity. The scenarios of the IPCC really come into different categories. There are ones that are driven purely by economic considerations. There's no regard to issues of pollution. You want to drive GDP up, you're going to put out massive amounts more energy than we presently do. Then at the other end, you have that they're driven totally by environmental concerns, and so you go very heavily for nuclear renewables. If you use fossil, you bury the CO2, and so on. And then, of course, everything in between. And then if you look at it from a totally global point of view, or do you look at it from regional issues? And so they have these scenarios that take into account all these different driving forces. And I'm sure you've seen these before. These are plots of the emissions in gigatons of carbon that you have to have as a function of time in order to meet a certain level of carbon dioxide in the atmosphere. And I'm sure you've seen these. You have to start pulling down the emissions quite soon, within the next 50 years, if you want to get down to only, say, twice pre-industrial times. We're not on any trajectory that people are doing that, incidentally. We're on a trajectory that, like that is our present reality unless people get their act together, as I'm sure you've heard. If you do the green scenarios, the environmentally driven ones, then the scenarios show emissions at that kind of level, show that with care you can in fact do that. On the other hand, if you let economics be in there as well, you don't meet it. If you just have total greed and burn the coal, burn the oil, put in all the nuclear you can, cut down all the trees, then you go through the roof, and heaven help us, Florida will be underwater, and so on. So they're different scenarios. Okay, what's interesting is to look at, in all of this, if you look at where we are today and where we might be in, say, 2070, this is a plot, and I'm not sure whether this is a superimposition of photographs from space showing light on Earth taken at night time all the way around, or whether it's a computer-generated one. I don't remember. Nakachevich showed this, and I just don't remember which of it is. But what you can see is, when you look at where energy is being burned, huge amounts on the eastern seaboard, huge amounts in Europe and so on, relatively little in countries like Latin America or Africa, and it's quite a lot in India, quite a lot in parts of China. But most of it is here in the developed world. If you look at these scenarios for energy use and take a typical one, and you look at 2070, it's changed. You still have these huge amounts of energy. We're even more energy intensive than we were before, but look at what's happened in India and look at what's happened in China. Enormous increases by 2070 that those projections have. And that's what we're interested in here, because the question comes, fine, so what is it you're going to use for that? One of the problems is that in order to meet their demands, if you look at Asia and you look at world oil demand, it's projected that Asia will increase the total amount of oil. They'll go from 15.8% to 24% by 2030 of total oil demand. China alone will be 10% of that, India 4.7%, and that's fine, except that oil does not come from India and China. And what you'll see is that this is already happening in both India and China. The amount of oil imports is increasing steadily to levels which are getting, like they are becoming, certainly in Europe, already in Europe, uncomfortable. And great concern, geopolitical concerns are being held hostage to OPEC. And so this is where some concerns come from. There is another major issue, and that is, in order to have all this oil or coal or gas or electricity coming, there's going to have to be an enormous investment. The IEA estimates that the total world investment for oil, gas, coal, and electricity is going to be, in the period 2001 to 2030, $16 trillion. And you have to ask, where does that come from? And who is able to raise that kind of cash and who isn't? And it's very interesting. If you look at oil, most of the money is required for extraction and distribution. Similarly for gas, though there's a lot required also for storage. Coal is nearly entirely in mining, and electricity, interestingly, is there's slightly more in transmission and distribution required than there is in generation, which is a surprising thing. One might have expected it to be entirely new power plants, but there's a major problem of being able to distribute the power if you install it. So these are the estimates of the IEA with that money. That would go globally. If you ask where it would go, a large chunk of it is in the OECD countries in North America, us and Canada. But if you look at, say, China is a huge amount. India is another huge amount, and so on. These are the ones we're looking at. And you have to ask, fine, where will they get that chunk, their fraction of the, where's China going to get $2 trillion from? Where's India going to get $1 trillion from? And that enters into issues of, are they viewed as reliable? And in fact, in both China, and one measure of that is how do domestic savings compare to domestic investment requirements. Countries that have high domestic savings compared to domestic investment are likely to go to raise the cash. Countries that don't, or are viewed as corrupt, will not. China and India actually do quite well in this. They have very high savings. So in that regard, they're reliable. Issues of whether governments are reliable is another one I won't get into, but there are certainly some countries, notably in Africa and some in East Asia and Latin America, that nobody will invest in, because they even if they have, they look okay from some points of view. The governments are so corrupt, nobody's going to chuck a few $1 billion in. So these are issues. China and India in this regard are quite well. Okay, I'm going to go quickly through each of the fuel sources and just skim over what the issues are for that fuel source. There is no issue of fossil fuels running out anytime soon. Just simply isn't. The reserve of fossil fuels in the world are huge, absolutely huge compared to consumption. There is no likelihood that oil will run out if you allow for all kinds of oil. There's a study by David Green at Oak Ridge National Lab, along with people here at UT, done a very nice analysis of that. If you allow for the development of the heavy oils, tar sands, and eventually shale oil, and allow the price will go up, oil is not going to run out in the next 50 or even 100 years likely. Even allowing for a massive increase in use. And also remember, you can make liquid fuels from gas, you can make liquid fuels from coal, and you can make liquid fuels from biomass. Liquid fuel is not going to run out because the world has run out of the capability to make it at a price that might jolt people here a bit more than it already has, but that would still be acceptable, particularly with more efficient vehicles. That isn't the problem. There are two problems. The first is not everybody has it, and so whatever you view as crises from the haves and have-nots are only going to get worse. And second is the issue, very visible issue of pollution. That's the problem. It's not the existence of the fossil fuel. Now, in terms of the pollution, technologies do exist for removal of carbon dioxide and for its sequestration. The issue, again, is cost and how much. It's not that you can't do it. But when you come to vehicles, it's tougher, because you can't do it in each vehicle. That's why people look going to hydrogen, even if the hydrogen is made from fossil fuels. Okay, you couldn't see that. This is the same thing. Just to put these are global hydrocarbon reserves and resources. And this is in gigatons of carbon. Over the period 1860 to 1998, the world used 295 gigatons of carbon in one form or another. The annual use in 1998 was 6.5 gigatons. The total resource base, not allowing for the more extreme kinds of things, is 6,760. You can divide that, and you see the answer is 1,000. So present usage with essentially more or less guaranteed in one form or another, most of it coal, there is like 1,000 years of fossil fuel at present use. So allow the fossil fuel goes up by a factor of 4, for example, heaven help us if it did, but allow that it did, 250 years. But that's not all the fossil fuel, because there are other additional occurrences, most notably methane hydrates, which are in the seabed, off the coast, and up in the tundra, running across Canada to Russia. Nobody knows quite how much is there. That's the estimate. And nobody knows quite how much you could extract economically, but that's, huge again. So the issue, the next 50 years, 100 years, even 1,000 years, is not likely that fossil fuel runs out. That's not the problem. The problem will be this one that some people have it and some people don't. That will change with time, because people will use up their fossil fuels. And the other one, of course, is the monstrous issue of pollution, that probably ought to have us not being quite as frivolous as we are today in its use. In terms of, if you did want to use it and you went to really advanced systems, you could extract and bury the CO2. It's just a question of cost. It's done today. This is not something that people don't do. A huge amount is already buried today. It's not you can't do it. But in terms of how much you can do, depleted oil and gas reservoirs, there's no reason not to chuck the CO2 back down the oil wells and gas wells. You already do it to push more oil and gas out. It's already done. You could bury 250 gigatons, and that would be 45% of all emissions projected on average to 2050. So you could do it. Of course, the bigger problem is, are the oil and gas wells where you've got made the CO2 is an issue. Because if you really have to move it a long way, it's not so trivial. There's a modest amount can be done in unminable coal beds, and that's worth doing because you release the methane which you can then use, which is cleaner than the coal. So there's good reason for doing that. And then there's a huge amount more that can be put in deep saline aquifers. And that is 20, depending on how much you believe in, is 20 to 500% of what we would emit to 2050. That's without going to the ocean. Now, whether you can sensibly go to the ocean to bury more is people still argue about. But you could likely bury the CO2 we'd use produce over the next 50 years if it was economically sensible to do it, and you could make the sources match the sinks. In the North Sea, in the Sleipner field, Norsk Hydro extracts 1 million tons a year of CO2 from a methane stream and buries it in a saline aquifer. That's going on now for 2 or 3 years. It's 1 million tons a year, just that one field. So you can do it. But all of this makes a number of people believe that one will move more and more to what we've been moving to, increasing the ratio of hydrogen to carbon, going towards the so-called hydrogen economy. Whether that will occur is not clear. But the attractiveness of that is all the energy sources, in principle, can be used to make hydrogen. The CO2, if it came from fossil, can be dealt with in a central plant. So you could make the hydrogen we wanted. You can make it, people looking at it for nuclear plants, high-temperature nuclear plants. We looked at it, in fact, in a study I did with people from TV and other places, just if you had a fusion plant, it really wasn't any different if you had a fission plant. But could you do it? Was it economic? And the answer was yes. If you can make electricity at an average of 5 cents a kilowatt hour, you can use off-peak electricity to make hydrogen. If you can sell it for, say, 2 cents a kilowatt hour peak for that amount. And you can, of course, make it from biomass, and you can make it from surplus wind power, hydropower, and you can make it from, of course, gas, which it mainly comes from today, and coal, and so on. So a lot of people believe that's the direction the world will go in. Renewable energies. Renewable energies were at one stage nearly everything we had, until people started using coal, and remained huge. And still today, 15% of all energy used in the world today is renewable energies, mainly biomass energy, trees, grasses, and so on, and mainly used badly. But technologies for use of renewable energies are increasing across the board, and this shows the learning curves for photovoltaics, showing the decrease in cost, wind power, decrease in cost, and this is gas turbines is another example of some decrease. People project that within the next 10 years, wind power is already broadly speaking, economic in good wind conditions with the big wind machines they have today. People project that solar is going to get down to around 10 cents a kilowatt hour. That's the projection for over the next 10 years. And there are other issues like what did you make the solar cells out of, and is the sun where you need the energy, and so on and so forth. But solar power is going to come along. They all are. In terms of what kind of resource you have there, the resource is enormous. And you look at all the sunshine that falls on the earth, or you look at the geothermal energy that comes out of the ground, it's huge, absolutely huge. But it's not technically available necessarily. It may be there. But if you look at current use of renewable energies, it's about 56 exajoules. I said it's about 15% of world energy use. If you look at the technical potential is 7,600. So the technical potential is 150 times bigger. So renewable energies, again, could in principle provide a lot of the energy, if not all of the energy we have, except, of course, again, you come back to it, fine, do you have them? If you're in Japan, what ones are you talking about? If you're in Korea, what are you talking about? You don't have much land left, you're not going to do much biomass, you have limited wind power in those areas. So India, very limited wind power, already using huge amounts of biomass. Hydropower already exploited maybe at the 50% level. And there are issues too. Many of these things are nothing is pollution free. You have to look at how you made it, you have to look at what it did to the land you put it on, and so on. But renewables are huge. Energy efficiency, I was asked this question before. Energy efficiency is critical. All of the studies that people have done that I've shown tacitly assume that in terms of energy use per gross domestic product is improving at 1% a year on average across the world. Everybody assumes that. In fact, you could probably do better than that if we really got our act together across the world. So we're already assuming it, but it is absolutely central. If you don't have that, you're just worse off. An example of the kind of things that can be done is I think, a fascinating example from the US. You take a standard 20 cubic foot refrigerator, you go back to like 1975, it used 1,800 kilowatt hours per year of energy. If you look at the same refrigerator today, you can get off the shelf, 3 years ago, it was down to 470, factor of 4, like nearly 3 or 4. For the same refrigerator, probably lower cost. And incidentally, at the same time, we got rid of all CFCs. And there's another factor of 2 or more available in better technologies, better insulation, cleverer design. So that's just an example of one thing. And you put that into lighting, and you put that into building design, put it into factories, steel manufacturing. There's enormous amounts still to be done. Fission energy. Studies by the group at PNNL and with other people believe that nuclear fission is essential for stabilizing CO2. Deployment of much more massive amounts of fission is essential. And particularly, they would argue, which you know more about here, I think, than I do, but you have to have a globally integrated system encompassing the complete fuel cycle, waste management, fissile fuel breeding, in order to be able to make this massive thing. The kind of things being discussed in the Gen 4 studies and so on. But it has to be on a worldwide basis. And everybody has to be a part of it. And the concerns about proliferation have to be handled internationally. But you'll see that countries like China and India are among the countries that need huge amounts of nuclear power, one way or another, as part of their portfolio. If you look at the uranium resources at different prices, what you find is that in order to, if you don't have the breeders and you're not making full use of all the uranium, you can't do this massive increase to thousands of gigawatts of nuclear. You're not going to do it on once through cheap uranium. I think this is, understood, even though there may be more cheap uranium than people believe. I think it was 10 million tons or something like that. You're going to have the full fuel cycle. You're going to have breeding to take advantage of it. And of course, you can also put thorium in as well, as the Indians are doing. And if you do that, then the study done by the people at University of Maryland, PNNL, looked at putting in, that's the use of uranium at different levels. I haven't got the one I wanted. Oh, well. I don't have, that's not the one I wanted. The study they did, it's the wrong view, right, looked at putting in, I think it was 3,000 gigawatts of fission plants by the end of the century. In other words, 9 times what we have today in the world in order to be a part of the contribution to reducing CO2. And they viewed that it was possible to do that with the uranium resources because you were using it properly. The interesting example of nuclear development is Korea. Korea imports 97% of its energy, 80% of imports are oil. The growth of electricity is 10% annually over the last 20 years, and they anticipate further growth of 5% annually through 2015. Their first commercial nuclear plant was operating in 1978. I think it was Westinghouse, was it? Westinghouse design, turnkey purchase here. They now have 18 power plants, including 14 TWRs and 4 CANDUs, and 6 of these PRWs are the Korean National Standard Nuclear Plant, which they make. I mean, essentially everything. The only thing they don't do is the fuel cycle, I think. So they've gone from 1978 to 2004 with no capability in nuclear to being having a power and capability in nuclear. It's very impressive, and it's a very interesting model for all the other countries that need this kind of thing that presently don't have it. In terms of Korea, they view fusion energy, because I can put a plug in for fusion here, as an important complementary part of the nuclear program. This is true for China, India, and Korea, in fact, broadly speaking. They view the two together. Fusion is another arm of the same thing, and they do them together, which I think is very, very smart to do. And I think the U.S. is coming around to looking at doing all that. This shows the evolution of the nuclear plants in Korea from operating in 78 up to moving to here. I can't do that, can I? From 1978 operating up till the present, and shows the thing. And this shows that the latest plants are the Korean National Standard Plant, and they're evolving even more. They want Gen 4 reactors. I think they're part of the Gen 4 group, I think. They will need Generation 4 fission reactors, and they, I'm sure, would hope to build them. And this is an important point. All these countries, it's fine for them to import these technologies up to a point, but eventually they're going to want to be able to make them themselves and sell them. And so there has to be a system in which they can do that. And they share in the development of them, but then they can make pieces. Okay. So I've just shown you that there's all the energy in the world. We can easily meet even the 4 or 5 times demand, so what's the problem? I'll come back. I've already alluded to it. The problem is sources of energy are not uniformly distributed, is the first problem. The second is all energy sources cause pollution. And the third is, in the nuclear case, proliferation is a concern. There is not going to be, people, certainly in this country, are not going to be supporting massive deployment of nuclear plants out of control in countries as we did before. Financing is an issue. It's a huge issue. We're talking about trillions of dollars. And these raise substantial geopolitical concerns. And I'll show you some examples of what they are. But on the positive side, what is critical is worldwide collaboration is a key to success. If we all work together on this in the world, then it's possible to have the distribution of these advanced technologies of all kinds intelligently done so that each country can tailor its demand to its resources the closer the ones it has. The problem is, as I'll say, is China does not have uranium, so it's fine to say China will have massive amounts of nuclear power, but then as they commented, we don't want to be held hostage to the uranium OPEC the same way we're held hostage to the oil OPEC. Now, it's slightly easier because you can purchase the uranium in advance and store it. Britain did that for many years, for example. But nevertheless, it's a concern. India, on the other hand, has massive amounts of thorium, and so they're developing thorium systems. Let's take China. China's population is expected to rise to somewhere between 1.6 and 2 billion people. This is up from estimates of a few years ago, sadly, when they were expected to stabilize at like 1.5 billion. They believe that their per capita energy consumption should arise to at least the lower level of that in developed countries, which is around about 2 or 3 standard tons of coal equivalent a year, which is about 2 tons of oil equivalent per person per year of energy, 2 or 3 tons. But if in fact you did that, then they would have to have a total energy 4 to 5 billion standard tons of coal equivalent a year by the end of the century. Well, let's put that in perspective. That's about twice what the US uses today. No reason it shouldn't be, but just to give an idea of the amount, we use far too much. They will be using twice as much of that, but with better arguments because they have five times our population. But that's a huge amount of energy. They project, and this is absolutely staggering, they're going to increase. They presently have 300 gigawatt electric of power in China. That's about more than half of what we typically are using. They plan to double that by 2020 and to at least 900 gigawatts by 2050. So by 2050, China is projecting that they will add as much electricity power generating capacity as we have. I mean, we have more than that, but in terms of what we typically use, it's in the range, I think, 450, 500. They're proposing to add that by 2050. No reason they shouldn't. We did, but that's a huge amount put in perspective. And then to go on up by another 400 gigawatts to 2100, depending on population growth. That is a huge amount of power. You really have to ask, what are the energy sources for that? What are you going to use? As our Chinese lecturer said, he said, anything that puts out less than 100 gigawatts is entertaining, but it doesn't solve our problem. So, they're talking about putting in, for example, you might have to put in 400 gigawatts of fission power. That would equal total world fission production today, if you did that. That then makes them the driver of cost of uranium in the world. Very uncomfortable position if they don't have it. So that's a problem there. What do I have on? Okay. The other problem is, if in fact they decide that that comes from coal, or a lot of that comes from coal, which they have a lot of, that would mean a coal use which is 3 times the coal use in the United States. We use 1 billion tons a year. They already use much more than us. But they would go to 3 or 4 times more coal per year than us. It's a huge problem. It's a huge environmental problem. It's also a problem that the coal is in the north population. So how do you move it? And they're very concerned about that. The other thing they have to be concerned about is that though they have a lot of coal, it's not a lot of coal if you're using it at that rate, maybe 70 years. As I said, the oil balance in China, they were exporting oil up till 1990. Now they import oil. Most of their oil is imported. It's increasing. What about natural gas? Well, they could get natural gas from other countries, and here's China. They can get it from Kazakhstan, and they can get it from Siberia, which they're already working on. In fact, those are possibilities, but it makes them hostage to those countries. And in the case of Kazakhstan, most of China's over here, and Kazakhstan's over here. You've got to move it quite a long way. That shows the same thing. Okay, there's another issue in China. This picture shows the yellow. The yellow is regions of high electricity usage, and the blues to the whites are regions of population. They don't match very well. So they have this issue of having to move energy into the regions where they have the people, where they don't have it today. Okay, in terms of what they're looking at every kind of energy source they can do. They will maximize all of them. They will go for Gen 4 reactors. I don't think they're a part of it at the moment, but that is an area they will be very interested in. They will go for the advanced coal plants with low emissions, like the U.S. Vision 2020 for a zero-emission coal plant. They will use renewables as much as they can, and they do also view fusion energy as a complementary and important part in the latter part of the century if it is developed. Now for India, one can say exactly the same thing for India. Population is expected to rise to 1.65 billion. The GDP is expected to increase by 62 times. They expect to use primary energy of approaching 4 billion standard tons of coal. It's the same story as China, nearly the same numbers. For the same reasons, they plan to increase electrical generation to over 900 gigawatts by 2100, so they have to add again a comparable amount of electrical energy to China. They're very concerned about emissions, but they argue that emissions should be judged per head of population, not per country. And therefore they have the right to emit a lot more than they are today. The same argument for China, because they are still relatively less than us. And that, to me, is a very persuasive argument. It's how much you emit per head of population. We argue that it's how much you emit proportional to your GDP. Well, their GDP will increase as well. So, but this is one of the sticking points in dealing with this. They are also interested in using fusion, the Indians, and to do it. Over the last 25 years, all of their energy, electricity, carbon emissions, group GDP have all gone up steadily. They've gone up in 25 years by a factor of typically 4. Over 25 years, GDP, electricity production, and so on and so forth. This is an example of projection for primary energy use as one scenario that was done. And what you see is that a huge amount of it remains coal. They have a lot of coal. It's not very good quality coal. It's also high sulfur content and so on. But they project as coal, and some of that, I believe, is no longer internally produced. It has to be imported. And they look at increasing oil and gas, and then they have nuclear and so on. So this is a scenario that would not be very happy making if you were worried about global climate change, and they're not necessarily happy about it, but it's what they see they might be able to do, which is an interesting reality. India's supply and demand is the same as China. The net imports today are something like 2/3 is imported, but it'll go to like 95% by 2030. They don't have very much oil, and so they're going to be importing massively. Electricity generation, again, the same thing goes up. It's coal. They increase their nuclear. There's nuclear quite a lot. But that's still coal-dominated. That's coal-dominated. In terms of stabilization, if you want to reduce the emissions and try and meet the 550 parts per million in the world, their contribution would be increasing renewable technologies, and if nuclear fusion existed, putting in nuclear fusion. By the end of the century, I think it's something like 70 or 80 gigawatts of fusion power. This would be some third or quarter of fission power at that time. So if fusion existed, they would use it. If not, this I think would be additional fission power. Now this is what I think is the most incredible view graph, and this is, so let's go back to gas, and let's ask, India wants to import gas, where is it going to import it from? And the answer is, it's going to import it from Turkmenistan, and it's going to import it from Iran, or it's going to import it from Qatar. And where do you run the pipelines? And you run them through friendly countries like Afghanistan and Pakistan, or Pakistan, you bring it into port in Pakistan. That's their option. The other one is liquid natural gas, And you can do that, but it's hugely expensive. The investments are incredible. I mean, they're more than the pipelines. And you waste a certain amount of the energy. Discussions have been ongoing between these countries. I heard about these discussions 10 years ago. Pakistan and India have been discussing for a long time running these pipelines. It's a serious discussion. And it might work because Pakistan would be paid a fee. The danger for India, of course, is that if they get into another conflict, Pakistan can simply close it off. On the other hand, if Pakistan does that, it loses income. You know, I mean, this is frank. I've heard a talk on this. Frank discussion of this. It's just reality. I mean, you know, Europe gets it from Russia, down through lots of other countries, you know, from many other places. All of us suffer that. We get stuff from lots of places too, and we assume that there's never any going to be a problem. But it's that I think is the most fascinating example of how serious this issue is for them of being able to meet their energy needs. That they can consider that. Was it Willie Nelson said, why do you rob banks? Because that's where the money is. Why do you get gas from Iran? Because that's where the gas, you know, Qatar, that's where the gas is. We looked at proliferation issues for fusion energy, only magnetic fusion, just as interest. We had an expert from ULIX. The bottom line was, as far as he could tell, within the present framework of international law on fission, there's nothing in fusion, magnetic fusion, that puts it outside what you already have to do for fission reactors. Yes, you have free neutrons. Yes, you have tritium and lithium and so on. Yes, you have hot cells, but you don't have innately uranium or thorium, and therefore it's quite easy to detect if you're doing something evil, because they shouldn't be there. So the view was that within the framework of the existing laws and treaties and under the IAEA, it should be possible to manage fusion. It will be no more difficult than managing fission. Inertial fusion we did not get into because that has other, as you well know, other issues. Okay, so conclusions of all of this are energy demand due to population increase and the need to raise standard of living is going to require new energy technologies and new energy on a massive scale, absolutely massive scale. If you take into account climate change, the needs become even more acute, becomes harder to do, and more expensive. If you're going to do it across the world, deploying the advanced technologies that are being developed, whether they're in fossil energy, fission energy, or renewable energies, or fusion, you're going to require global development. One interesting example of this is in the fusion area is the International Thermonuclear Experimental Reactor. We heard a talk on that. The partners in that, as I'm sure you know, are the European Union, Japan, Korea, the United States, Russia, and China. And India is reputed to want to come into that deal. It's hovering on being built or not being built because the Europeans and the Japanese cannot agree on where to put it. That may get resolved soon. But that would allow one to at least see something about the prospects for fusion. But it's an interesting model for how countries can get together to design something, pay for all the research jointly, and all own the results to some level, and be in a position for manufacturing components and so on at a later date when that led to something that was commercial. It's the same model, might be interesting for fission. I mean, it's like the Gen 4 collaboration or the ones for fossil. All energy sources will be required to meet this need, all of them. And it's only an issue of what you have and what's available to you, and your geopolitical concerns determines what you have. The United States really doesn't have an energy problem. We may have a lack of judgment in what to do. We don't lack energy resources. We lack intelligent use of them sometimes, frankly. And that can be changed. I mean, we still have time. We have huge amounts of fossil fuel. We clearly can do fission. We have large resources of renewables. And we have technological capability to do anything we want to. But that isn't true for many parts of the world. It just isn't, and particularly where a lot of the population. It's not the increase in electrical demand will mean that a lot of new plants are required, and of course replacement plants. And this is an issue for fusion energy. As one person raised, well, if you develop it in 2050, who will want it? They've already got what they need. What I just showed you is no, they won't have what they need. They'll still be increasing, and you'll need to replace older plants. So from that point of view, from the fusion interest of this workshop, that isn't an issue. If fusion exists, people will use it if they need it. And in that regard, from fusion energy, is an interesting potential option for many of these countries, including China, India, and Korea. Thank you.
Okay, we have time for questions and comments.
A couple of questions. For example, on biomass, making alcohol from corn, for example, or some other, the Europeans will use rocks or something like that. But what is the energy balance on that? In terms of, by the time you make the fertilizer and you drive your diesel tractor and harvest it, it seems like it.
My memory is on modern systems. It's like 4 or 5 to 1.
So
that's my memory.
Energy payback is about 5 to 1.
4 or 5, something like that, maybe 3. I mean, if there is an energy payback, but I think in the early production of it, it was highly questionable, is my understanding. But I think nowadays there are modern systems. The other thing is there are other technologies being developed. I know one person who I think has very good judgment who believes that in fact the logic with the biomass is to gasify it, and that will be the most efficient way to use it, regardless of whether you convert it, you just use it to make electricity or you used it to make a liquid fuel. And I suspect that person is right, rather than fermentation processes, and I suspect that person is right. Corn is not necessarily the best thing to use.
But there are other things. And then also, like in California, there are many windmills east of San Francisco. What is those were put in with tax credits.
They were also put in, I suspect they were put in inappropriately with tax credits. They're very old. They don't represent a modern windmill. And you have to look at, say, the advanced ones that have been put in Denmark. Denmark, 15% of all electricity now, I think, is wind power. I think it's 15%, and they're raising it. And you look at modern wind machines, they're just totally different. I talked to a guy who was a wind expert, U.S. wind expert, called Paul Geith. He's written a number of books you might want to read, GIPE. And he said if you want to improve the prospects of wind power, you would destroy Altamont Park and you would destroy Altamont Park Pass by Livermore immediately. He said it's terrible. It does not represent wind power. It represents 30-year-old technology. It's inefficient and inappropriate. So they're not good examples, I think. Modern wind machines are different.
Improvements on helping the windmills to windmill killing birds?
Yes, the main. Yeah, I know. There are 2 problems. The main problem there are 2 problems. One is you put them on migratory route. Not very smart. That's the first problem. The second problem, though, was a really big one. Was you look at the old wind machines, birds could sit on them. They had bars and things like an oil drilling derrick with a thing stuck, so the birds would sit on them, and then the birds would fly down, and they don't see the propellers, they don't see the wind machines. The new modern ones, there's nowhere for the bird to perch, and they're out to sea.
That the modern windmills don't kill birds?
No, I didn't say that. I said they are. You asked me whether they were improved. Was your question? The answer is yes.
So perching.
A lot of things kill birds. You kill birds when you drive on the road,
Perching minimizes the number of birds.
Yeah, particularly the raptors. One of the biggest problems with the raptors would use them to look for mice and so on, and they would fly down through the blaze, and that was a huge problem. Mm-hmm. And it is an issue if you put them on migratory routes. But a lot of them today are out to sea, being put offshore, out to sea, and they're not necessarily on migratory routes. It's not the same problem.
Yeah.
They don't have to go on fast.
You had one reference, as I recall, or a couple of references actually. But you have references for like energy balances on wind power and techniques.
I think wind power is very high. Wind power is very high.
Payback.
I don't remember the numbers, but they're pretty good. They're pretty good. The modern wind machine is 98% available capacity.
I was recently
the things are 300 feet high. The blades are bigger than the football field across, made by GE.
I was recently in Germany, and there are thousands of those things they've installed already.
They're not, again, probably not a good advertisement because they did it for tax reasons in not good wind areas. And if you want to put them, you put them off the coast of Britain.
Yeah.
and places like that, or in the Central Plains here, where there's good wind power, and high-level wind power. There's nothing much else going on, and there's a huge wind potential.
So the footprint of a nuclear plant is far smaller than some of the options. And for example, if a wind turbine makes 1,000 megawatt on the wind blowing, 1,000 megawatt plant generates as much as 100 of these.
You have to be very careful with those arguments. I think any of the renewable energies is lower power density than a concentrated one. That's true. Solar, for example, wind power, geothermal, certainly, and so on. However, when you take a nuclear plant, you need to look at the uranium mine as well, the trains that move the uranium ore, the plants that can do gaseous diffusion plants. You've got to make like and like. You have to be a little careful, but there's no question that say the concentrated fossil ones and nuclear are a bigger concentration.
The other argument about not ever running out, I guess you never really run out of it. It gets more and more expensive to get as they go to alternatives. So
well, you have to be careful here, because somebody pointed out if you increase use of oil by 1% a year for some length of time, at some point the amount of oil you use a year is equal to the volume of the Earth. So clearly that couldn't have happened.
that's right.
It's actually a surprisingly short length of time.
Well, I meant you get alternatives that cost less. You can go after those.
Yeah, but I think the numbers I've seen. I don't work on any of these. The only one I've worked on really basically is fusion. But if you look at any of the, my train of thought now. Oh heck. Oh yeah, all of these have the potential to come down. Just take electricity, to say 4 cents a kilowatt hour, except possibly solar. All of them do in the right place, and 4 or 5 cents a kilowatt hour, which isn't necessary. In fact, you could well stand more than that. Many people do. So they can all come down, and you'll use them where they make sense, and you'll take into account everything pollutes, everything, and you just have to decide which of the various bits of the pollution you wish to put up with. Frankly, I mean, power lines aren't wonderful for birds either. For example.
In the fusion business, what do you think the probability of a successful fusion technology being developed in 50 years?
It's a question of money.
Think so?
Oh yeah. I mean, the issue. I don't think there are really major physics issues for fusion like there used to be. You go back 20 years, 30 years. People see solutions, whether inertial or magnetic, to nearly anything. You need better physics because you want to make it more economic. The materials issue remains a huge issue, but there are workarounds on that for the neutrons. There are workarounds for that. If that really turned out not to work out, there are solutions for that. They might make the physics harder, but there are solutions. And the other one, I think, is the issue of availability. It's I mean, look at anything we have today, it's very complicated. And so requiring that it has 75% capacity factor. At the moment, you can only say what you need to have to do that. You know, this component must last that long, replacement time like that. You can't prove it. Until we've built ITER and things like that, it won't be possible to get a judgment of those kind of numbers. First judgment. Oh yes, no, I see absolutely no reason it can't be done. But it's $30 billion, you know, it's $25–30 billion, and we said this many years ago. It was actually some billions more, but we spent those billions. We did what we said we would do, broadly speaking, and it's that much less, you know, what we said 30 years ago, less what we spent. Hasn't changed. If you don't spend it, you can't develop it.
Larry?
What's the probability, you think, of this doomsday scenario where this whole technological civilization collapses and we go back to forming the states?
Ask somebody, you know, ask Dick Cheney.
Well, I mean, there are...
Or Robin Williams, Mike.
Yeah, no, but there are some, I mean, we do have some fairly vulnerable issues, I think, with regard to being able to sustain the oil imports, for example, if tariffs were to blow up all the oil fields in the Middle East and a variety of things, it's collapsible, I think. I mean, I think that what we see as our society today is somewhat vulnerable. All of the certain things, manufacturing, high technology devices and so on are in certain places, you blow up a few key facilities, and can we sustain it?
I don't know.
I don't know, I just think...
I want to read, there's a very good paper by Amory Lovins. You read Amory Lovins?
I try not to.
Well, no, he wrote a very good paper. It was commissioned by DARPA or something like that, the Defense Department. He wrote back about the beginning of the 80s. He wrote it on the issues of terrorism and catastrophic events and things like that and vulnerabilities. It's a fascinating paper, in fact. He did it for the Defense Department.
Yeah.
You can probably find it on the web under Rocky Mountain Institute.
Yeah.
Under his institute. It's worth reading. I mean, for example, if you take, I think it was a liquid natural gas thing in Boston Harbor, one of the centers where there's others in Tokyo. If you were to hit that correctly with something, it's equivalent to 300 kiloton hydrogen bomb.
Well, it seems to be like the world could get ever more sophisticated and higher standards of living if we mind our P's and Q's, but it seems like it's also very possible that we could go the opposite direction.
Yeah, our biggest danger is the haves and have-nots. If we don't work to raise the standard of living of the people who don't have, we're really in trouble. We are really, truly in trouble.
Let me make a comment before we adjourn. John has been giving presentations in our department for a long time, over many years. And he always presents, first of all, let's recognize that he's one of us. He's an engineer, he's a fusion person. Yet he presents information in an unbiased way that causes us to think. And today I think we've gotten information like that. And we need more presentations to generate more discussion like the one that we had today from John. And so with that comment, let's express our appreciation to him. And we have refreshments downstairs, and we can continue the discussion down there.
Can we get the visual?
Sure. How much money is that? I'm just joking. We'll give it. Yeah,
I need to get my seat.
I've got it.
Okay, you can.
You think you could find that missing slide? That seemed like a key one that would be of great interest. About uranium depletion or...
Yeah,
3,000.